Okay, so today we're going to do Poisson distribution. So our CLC is I can determine the Poisson distribution. It's fantastic because all I have to do is change the binomial to Poisson. Awesome. Okay, so you have to know when to use each type of distribution. So for binomial, how did we know to use the binomial distribution?
There were two things.
Only two events. Yeah, there were good. Only two events, and each trial is independent. So Poisson, you have to know when to use Poisson. Now the nice thing about Poisson is they tell you it's Poisson distribution. So binomial, they expect you to figure it out. Poisson, they tell you. But this is the type of thing that it can apply for. There are always things you can count. So my examples are number of goals scored in a soccer game, number of cars passing a toll gate in an hour, number of white blood cells found in a cubic centimeter of blood. Okay, so something that you can count. They're not going to be continuous values. Other things that have to be true. So number one, we've already kind of said, the event is something that can be counted in whole numbers. The occurrences are independent, so that one occurrence neither diminishes nor increases the chance of another. The average frequency of occurrence for the time period in question is known. So basically you have to know, on average, the team scores 5 goals a game. So you need to know how many they score and in what interval. Okay, so number of cars passing a toll gate in an hour is fine. If you know it for 15 minutes, it's fine, because then you can just multiply it times 4 for whatever your scenario is. So that's the only parameter that you have to use in Poisson distribution is the average. Okay, and then the last thing down here says it is possible to count how many events have occurred, such as the number of times a firefly lights up in my garden in a given 5 seconds. Some evening, but meaningless to ask how many events have not occurred. So, how many times did the firefly not light up? Doesn't make any sense. How many cars didn't go through the toll booth? Doesn't make any sense. Okay, so it only makes sense to count how many do. Okay, so the big deal is you're going to have to be able to know the average number in a given time period. So I have a couple of weird long things here, but they were just examples you and I. Some examples I stole from Stanford. Okay, so I'm just going to read them to you. It's just to kind of give you a feel for the type of distribution. So the first one, the Poisson distribution has one parameter, and you see a lambda there. It can be other symbols sometimes, but it's always just the mean. Sometimes they use it down. I have old questions and new questions on your problems, so they'll use different variables sometimes, but it's always the mean. So this parameter describes the expected mean number of events. So let's say we have 100 apple trees, all identical. During the harvest season, we put a basket under each tree and we catch a few apples a day. Let's say the average is 2 apples per tree. The Poisson distribution is basically going to be a formula that tells us how many of the baskets we should expect to have exactly 2 apples each day. 0, 1, 2, 3, 4, and so on. If they normally get 2, the highest probability is we get 2. It goes to infinity, though. So, believe me, the probability.
Like of getting 999 apples in one basket.
Exactly. And that probability is going to be teeny tiny. It's not very likely if on average you get 2, that you're going to get 999. Okay? But Poisson distribution does go from 0 to infinity. So that's going to be an important thing. So, as long as each tree is identical, or close enough, about the same, and as long as each apple's fall into the basket is a separate and independent event, and Tanner doesn't go and shake the tree and try to make his basket come out to be more, then we can expect the Poisson distribution to do a good job. However, if there's something else, if there's a sunny row, or there's rain, and have you ever seen rain when it you can see where it's raining, where it's not raining? So some of the trees get rain, some of them don't. So if there's different conditions, then we can't expect the same results. So you need kind of fairly consistent conditions. Okay, so that's one example is apple trees. The other is a physics one. But a process that may be more easily fit the model is the capture of neutrinos, a tiny subatomic particle, from the sun in a special detector. Every day the sun emits the same number of neutrinos, and each neutrino has a small but constant chance of hitting the detector every test. If the average count is 2, the Poisson distribution tells you how likely you are to catch any number you want in a given day. So if you know the average is 2, what's the probability I don't catch it? what's the probability I catch 20 today? You can find the probability of catching however many you want to try to figure out. If the single day's neutrinos have a Poisson 2 distribution, meaning the 2 just means that's the average for a day, then it seems reasonable if you checked the machine every other day, how many would you expect to find every other day? 4, twice as many. Okay, so as long as the events are independent, the Poisson distribution of A plus the Poisson distribution of B equals the Poisson distribution of the quantity A plus. So basically, if they change the time period on you, just multiply the average or divide the average to make the appropriate ratio for the amount of time.
Okay. Well, this is what the Poisson distribution looks like. I don't have either one in color. That is just sadness. Oh, that would look pretty.
Either one of you.
Apple Boy,
I just learned some incredible news.
are you going to share it with us?
Yeah.
Okay.
A dude in Colorado was hiking on a trail when a mountain lion attacked him and fought it off and killed it by strangling it to death. And now he's in the hospital getting better. What a laugh. I wish I could do that.
I do not wish to do that.
Good for
I'm going to pass on that one. Okay, so this is just, remember I showed you the binomial distribution graph? This is just showing the graph if you had different averages. And so if you look at the very first one, I'm just going to put a 1 by this. It's erasable pen, so you can erase it if you want. So this is basically if on average you expect 1 in any given time period, so you expect 1 crazy outburst from the class per hour. That's on average. Okay, and so okay. True. Perhaps I have the time period incorrect. Then you expect the highest average. Now that's not all the time. That's not all the way up to 1. It's not 100% of the time, but that's where you expect the peak to be. Is whatever it is on average. So you got a pretty good chance of getting none. But the farther out you go, the probability of having 20 outbursts, if you only on average usually have 1, is not very high. But it still exists, so this goes to infinity. So what happens is if they've asked the probability that you have more than 9, you can't go from 9 to infinity because this is a finite formula. So you would have to do the complement. You have to say 1 minus what's below 9. And I'll do some problems like that. So the point of this is just really that you can see for the 2, it should be centered around 2. For the 3, it should be centered around 3. And you can kind of see how this shape of the graph looks like. But you expect the peak to be at whatever the average is. Okay. And this is just a cumulative distribution. So they're adding up. So this is the probability of 2 or less when you look at this. And so they have it for different averages. So these each represent the average that you're expecting. So if you expect on average to have 15 outbursts, okay, then you got a pretty low probability of having 2 or less, 4 or less, or 6 or less. But by the time you're getting closer to 15 or less, you're starting to get a pretty high probability. And this is approaching 1. You know, the probability that you have like 1 million or less, the idea is that the whole thing approaches 1. Okay, so you can just kind of see how the cumulative changes based on the average. So you see the middle of it, like the middle of this kind of looks like around 15. The middle of this kind of looks like around 5. It's almost to its halfway point when you look at the cumulative distributions. You never have to do that. I just find the shapes of them to be kind of interesting. So perhaps you'd like to actually do something with the formula. Okay. These are the formulas that are on your formula sheet for Poisson distribution. They will tell you, they will say, this is distributed as a Poisson distribution, or they will use this symbol. So this is saying X, and the little squiggle is distributed as the PO. So that's capital P and lowercase o. That just means Poisson. It's not like a 0 or something like that. So it's Poisson distribution. The only parameter is M or the average. So they're using M on the formula sheet. I said lambda a minute ago. But typically you'll see M or lambda. I think it might use lambda in the book. Here it says you can have mu or lambda. So sometimes they use different things, but the only parameter is the average of a certain amount of time. And to figure out the probability, you're going to put in the number of successes or the number of times you're expecting.
0, 1, 2, 3, it goes to infinity. So the x is the probability of the event happening 0 times, 1 time, 2 times, 3 times, and so on. So the x is how many times you're trying to see the probability of it happening. The m is just the average. E is just our friend E, 2.72. Okay. And so you just plug in that formula and it gives you the probability of each particular value. Notice it is also telling you the mean and the variance. Not too hard. The mean is the average. You don't have to do anything. The variance is considered to be the same as the mean. And then if you want standard deviation, what do you have to do that? Okay, so you see though, like this isn't, even though it's common sense, you're not necessarily going to remember this for every distribution, but you're going to go look at it. So here's the problem we're going to do. Also, your calculator does this, but you know IB, they're going to make a situation where you have to set it up and you just use your calculator. And they may let you use your calculator sometimes. Apple boy?
No comment. I want you to know that David Carroll liked the tweet where I threatened to fight. He liked.
He should have. He should have also retweeted it.
He should have, but I'll take what I can get.
Oh, no, he definitely. That was my favorite tweet in the last Twitter. So, my other one was probably some other one you did.
Yeah.
Which I only see because I guess I don't follow any students on Twitter, but I guess Leslie Sharp does, and she's in my
she
feed.
follows me.
And it says like fun.
Yeah, so then like I can see the discussions.
There's some pretty crazy things out there on Twitter.
Yeah. Sometimes it's better for me not to know what all is out there. But anyways. Alright, so here's our example. Police use speed cameras to record the violations of speed limits at a strategic spot in the city. The installed camera pattern automatically turns itself on average every 10 minutes. The pattern follows approximately based on the Again, they're going to tell you that. You're not going to wonder, should I be using Poisson? The only one they don't tell you is Poisson. So then it says, within a 10-minute interval, what is the chance that it is on once, twice, and at least once? So they did give us how many times the strategic spot automatically turns itself on average every 10 minutes. So once every 10 minutes. Is that what I'm getting out of this?
I think that's what we're getting.
Okay, so that means that my average in a 10-minute interval. Now, if your interval changes, like it's going to down here, it's going to change your average. Okay, so they gave us that. That's all we need to figure it out. So I'm going to say this is a Poisson distribution with an average of 1. Don't need an equals. Okay, and then they want me to find the probability that it is on once. Well, I'm just going to write the formula above it because it's way up there on my sheet. It's m to the x e to the negative m over x factorial. That's an m. So if you want the probability that it's going to come on once in 10 minutes, I would expect this to be the highest probability I got.
So is the, when you said m equals 1, is that talking about the mean or minutes?
Okay, yeah, so this is the mean, and this one is what I want to know the probability of. So unfortunate that they're both ones in this particular case. But this one is going to be the m, and this one I'm trying to find the probability that it happens once, so that's an x. So for this guy, I'm expecting a decently good probability whenever it's the average. If it's far away from the average, I'm expecting something pretty tiny. Okay, so this is just 1 to the 1, e to the negative 1 over 1 factorial. It is. This is AI. Why do I have to use all that? That's the formula for a Poisson distribution. They told me it was.
Wait, can we go over
It is something that you can count every time. So Poisson has to be something that you can count, and each thing has to be independent. But they also are going to tell you if it is or not. So if you were trying to apply it to your own situation, you would have to know you can count it, and you would have to know it had to be something you could figure out the average number of times it occurs in a given time period. Those are the two main things, yeah.
So the two ones we have in this equation, I get that one of them comes from, it just like what is the
The
chance
average.
of it on ones?
The other one, yeah, this is the x.
Mhm.
The other one is because it said it came on average every 10 minutes, so it's once every 10 minutes.
Okay.
So the average was 1.
And if it said, on average, every 5 minutes, and the question stayed the same within a 10-minute period, would it be 2?
E to the negative 1 is about 0.368. So that'll be the highest probability you'll get for any situation. For twice, that's just going to change to be the probability x is 2. The average doesn't change because we didn't change the time period. So you're just going to substitute in. So I'm going to have the average is still 1 to the 2, e to the negative 1 over 2 factorial. So that's just basically a half e to the negative 1, which is, yep. So 1 is the average. So this guy is always the average. And then this guy is always the x. Yes, that is exactly right. Okay, so she's on to me. For at least once, that means greater than or equal to 1, which means you'd have to add up from 1 to infinity, which is ridiculous. I agree. So
Or you could just do it for 0 minus 1, could you?
you're exactly right. So we're going to do 1 minus the probability of 0. You always have to do that for Poisson. So 1 minus, and this time we're putting in m is still 1, x is 0. Taylor, I think I like you being in the front.
Because it's not just up to no good.
Because I feel like you're like with me instead of like just like, you're always like doing something, but it's like figuring out a world problem sometimes. It's not necessarily like my math problem. So you're like an alert, astute fellow, but now when you're up here, I feel like you're astute with what I'm doing. I mean, you were just invited. Yes.
Yeah, I don't know.
Jeez.
It's more than racial discrimination.
How is it racial discrimination?
I think he said racial, not Rachel.
It sounded like
But it did sound like racial discrimination. You would just. Okay, I do want to show you can do this on your calculator. So, menu, probability.
Wait. I didn't write that down.
What, that?
Yeah.
Okay. Sorry.
I got distracted by Tanner.
So the probability of 0 is the same as the probability of 1 in this situation? Right? Or not sure.
Yes. Or is it? Yes, it is because n is 1. Well, I have to look because 0 and 1 cannot be same.
Wait a second. So n is the average.
Yes.
Okay.
Okay, so if you go to menu, probability, you're like pressing buttons or picking up calculators.
5. That's what you start with.
Have to wait for everyone to get calculators.
Oh,
Tanner, can you get me a
what
password?
color?
I mean, while I'm in, it doesn't matter.
Yeah, but why does it matter what number it is in the slides?
I mean, some
The
people
color.
are
The color.
That's true.
Also,
That was
they say
considerate
the
to us.
calculator, though, so.
We'll have to maybe make an improvement.
I was trying to do
Not really, actually.
Alright, menu, probability, distribution, same as yesterday. Poisson is towards the bottom, so you can scroll down the bottom or you can arrow up. And I'm going to do a Poisson PDF. And this works the same way as binomial. The CDF is just
there's only one parameter, which is only the average. And let's just say we want to do the one that was 1. And just put it in and visit all, please.
Can I point out something cool in the calculator?
Yes.
So, menu, top, arrow. It's like Jack Paws, because it's J and then
Oh.
It made me think of him.
Nice shout out for Jack.
So, you know anybody in Virginia?
What?
You know anybody in Virginia?
I was born in Virginia.
Really?
Yep.
Numbers on the
Whoa.
board.
Bring on this money.
All right.
I know a couple of people who go.
Oh, I like that
My
too.
grandma. Not from Virginia. Oh, wait. She's still not. That is.
Oh dear. Okay, now the problem changed and it said within an hour, what's the chance? And it's the same questions. So what's the only thing that I have to change?
Oh, it's 10. I was thinking 15. You're talking about 15.
So I multiply. Okay. So if it's one time in 10 minutes in an hour, it's going to be an average of 6. Okay. So it'll come on 6 times to every hour. So you're just going to do the same thing only with 6. Okay. So it's a Poisson distribution with an average of 6. And so same questions though. So x equals 1.
Show top of the board.
Sure.
Okay.
So m equals 6 and x equals 1. P of x equals 1. Oof. 6 to the 1. E to the negative 6 over 1 factorial equals, then multiply.
It's 0.04872.
0.0149.
Why do we put P?
Point 0.149.
Probability that you get it once.
Oh wait, no, she's saying
It's like every time we write it twice, we're like P.
Oh, there was literally no reason for me to do that.
Okay, it's like not.
it looks
Yeah,
good.
it's not a thing. I just keep doing it.
Just looks
No, it's
nice.
not a thing.
Okay.
All right, somebody gonna do the other two?
Oh, 10, man.
Oh, I got you.
Oh no!
And then you can do the one for at least.
Because you didn't do this.
Okay.
Hey, Rachel, can I do the 3?
Can you what? Sure, I don't care.
What?
Okay.
Yeah, you go there and take
Okay. X equals 2. So. And what is that?
0.0446.
Beautiful. It's all you. Yeah, you got it.
And they should all add up to 1. So Tanner, you can do that one without even doing the formula.
You think so? Oh, no, that's cheap. You're thinking I bring my notes up there so it's up.
I don't think you can do it without.
Well, aren't all 3 of the things supposed to add up to 1?
Oh, we can't get distracted. Okay, so we're gonna go 1, 2, 3. There's 3. And then, you got that, Sam?
Yeah.
Alright, man. We gotta go with the whole P. X is greater than or equal to 1. And then that also equals 1 minus P. Wait a second, is this the same? No.
Yeah, it's the same thing, only we have a different name.
Oh, yeah, so it's 6. Wait, no, we got 1. Because there's a 1. Minus 6 to the 0. B minus 6. All over 0 factorial.
And it's 0.998.
0.998.
Well, that is true. It's pretty close. Don my stuff back.
Neither one of those is my favorite. I like Butterfinger more than either one. I guess I'd go 100 gram over Baby Ruth.
Really?
But you are more than welcome to.
Hey, so
I don't think either of them are good times.
Yeah, I
Just
don't
think
think
that
it's.
just-
I don't think it's.
we'll go 100 grams, because that one looks like it's been really
I have a song
It's so real good.
Okay, so this first part is just the calculator directions. If you forget, you can go back and look at the document, but we've already done that. So this one's going to be pretty easy. It says the number of radioactive particles released per minute from a meteoroid after it enters the atmosphere is recorded, and the average is found to be 3.5 particles per minute. So this is my M as long as they don't change the time period. Okay, and then it says find the probability at any 1 minute, so they didn't change it, so we're good. There are at least 5 particles released. So what happens here is you have a Poisson distribution with an average of 3.5. And they want the probability that at least 5, so greater than or equal to 5. And how are you going to have to do that?
Minus, like, 4.
4, 3, what else? Yep. So everything between 0 and 4. So you'd have to subtract 0, 1, 2, 3, and 4, but there's a cumulative function on your calculator. So you don't have to do them separate. So it's kind of going to look like a Poisson, and they don't want like calculator notation, but you're subtracting it with an average of 3.5, a lower bound of 0, and an upper bound of 4 is what it's going to look like on the calculator.
But it's the same as subtracting probability 0, probability 1, probability 2, probability 3, probability 4.
And it's PDF or CDF?
CDF, if you want to do a bunch at one time.
So what did we say the average was? 3.5.
And notice that the defaults to a lower bound of 0 doesn't mean it's always 0, but it does remind you not to leave off 0, because it's really easy to leave off 0. And you just want to start with 0. It was 4, wasn't it?
Is it 4 or 5?
It was 4, because it was greater than or equal to 5. Okay, and so you can just do that all together and get 0.275.
0.27.
5. Good. Alright, we just have one more, but it's one of those multi-parters. Yeah, it was greater than or equal to 5, so I did 1 minus the probability it was between 0 and 4. Excellent. Last one.
You know, with just a few parts.
This is the last one.
Last
Let's go past it.
Alright, small aircraft arrive at a certain airport according to a Poisson process with a rate of 10 per hour. So that is our average
As long as they don't change the time period.
Can we pretend that this is the Berlin airlift?
Sure.
What is the probability that during a 1 hour period, 8 small aircraft arrive, at most 8 small aircraft arrive, at least 9 small aircraft
Okay, so for A, I'm going to say that this is a Poisson distribution with an average of 10, and I'm going to find the probability that X is 8. And then I'm just going to write out all of them. We're going to do the probability at most 8, so what would that look like? Mm-hmm. And then if I want to do a cumulative, what is that going to be in between?
0 and 7. So it has to be less than or equal to, right?
Yes.
You couldn't do this less than 7.
You got to include the 8. At most 8, so that includes 8.
Could you do less than 9?
Well, no, because, I mean, yes, yes, less than 9, but then you'd still have to do this. You can because it's countable.
Is
Yes.
there going to be any more cold this year?
Cold?
Yeah. Are we going to get any more snow?
I'm liking it.
Yeah, no, I like it.
Like it.
I like how it went
It's totally
from
okay with
0
me.
to 100 real.
Like if it's not going to be snow where we're out, we might as well have gorgeous weather.
Exactly.
Okay, so I'm going to do these two on the calculator. And it's looking kind of crowded, so I'm going to get a new page. So we're going to do menu, probability, distributions, and do a PDF for the first one. And the first one was an average of 10, and we wanted to find the probability of 38. That seems like it'd be a decent probability if on average you get 10. Okay, so 0.113 is what I got for that one. And I'm going to go ahead and put in less than or equal to 8. I can see that you're all riveted by this cumulative distribution. Meaning not caring at all. So let's go 10 from 0 to 8.
Is this for a different part?
Yeah.
This is not for
This is II. 0.333. I'll go back so you see what it's. Okay, so I did kind of two at once. So I did the I, and I did the II.
So this is the. Oh, so is this mainly going to be like a calculator thing, or is it going to be?
Yes, but you know how they can do stuff. Makes you go to the formula because they want you to solve for something weird.
You've heard of parabola. You've
Yes.
heard of hyperbola.
Yes.
Have you heard of orange bola?
Oh, like it.
Also known as Halo bola by the orange activist movement.
Nice. Good to know.
It is
Okay, the probability that at least 9. How could I write that?
Greater
greater than or equal to 9.
Okay. So I know I can't go in the greater than direction because I can't go 9 to infinity, which, by the way, you can do on continuous distributions, but not on discrete. We're not there yet. So it's got to be a 1 minus. So 1 minus what?
2. Like this.
Zero
Yeah.
is
I.
less than or equal to X is less than or equal to 8.
Which we already did.
That's just
Stop.
She just snapped for me, but it was really weird.
Why was that weird?
They were so, they sounded so nice.
Honestly, that was a little bit of a weird story.
They sound so,
It is
I
good,
don't
yeah.
understand how you sound so good.
It is
Wait,
good.
how do you guys?
No, like I'm not saying you stopped it. It's just funny how you were just going at it.
I snap for people pretty often.
Is that like a celebratory thing?
Yeah, it's like instead of clapping, it's like this one is something good, it's like snacks.
I like that. You have not. You does have nice snacks.
It's because I do it a lot.
Literally. And
Do it
something.
Do you want me to do it more? I don't do it a lot.
No, I just want
They're like so soft and nice.
to. It just looks like it's just.
It
happening.
flows.
It sounds like I'm in a poetry bar. Like,
Yes.
Exactly.
That's nice.
All right. So here we go. What is the expected value and standard deviation of the number of small aircraft that arrived during a 90-minute period?
Oh, we have to
And
change
at
the
first it says.
Oh, change the M. Okay.
Where's the?
I agree.
Yeah.
What's there been?
Wait, how many was it at first?
It was 10 and 1 hour. So an hour and a half. 10 plus 5. Should be 15.
No, 15.
No. Okay. Now,
standard deviation would just be the square root of that.
yes. Okay. And so it tells you that expected value is the same as the mean. And it tells you that variance is the same as the mean on your formula sheet. So you are exactly right. Standard deviation, you just need to take the square root, which is about 3.87.
So when it
3.87.
says what's the expected value, does that just mean
Yes. So this, the mean and expected value are used interchangeably, which is
I
kind of
always
an,
forget that that's one of the
yeah. All right, we're working our way down. What is the, we are. What is the probability that at least one small aircraft, so we want the probability that's greater than or equal to 1, but it arrives during a 6-minute period. So, yep. So a 6-minute period is just 1/10 of an hour. So it's 1/10 of whatever you got in an hour.
Just 10.
Uh-huh. There you go. So this is a Poisson distribution with 1 for the average. Now, how do you figure out greater than or equal to 1? You can't do greater than. Yes. And so I'm going to do that on my calculator. By the way, they're saying the flus are starting with non-stop sneezing.
Listen. I use the sanitizer in every class I walk into. And
Okay,
I
so
also got the flu shot.
I did too, but some people are getting it that had
The
the.
super flu, like
I don't get my thing.
theoretically, if you get the flu shot, even if you get the flu, it's not as bad.
That's true. Okay, so I got 0.632.
Whoa. Why are we doing that?
Because we were trying to find the probability that there was 1 or more. And so that's 1 minus the probability of not having any. So that's what I put in my calculator, was 1 minus the probability of not having any if the average was 1. Okay. The next two parts kind of go together. But it says, what's the probability that one small aircraft arrives during 2 6-minute separate periods? Okay, so it could be like either in the first.
Was it the one that we just did? Like an aircraft showing up in 1 6 minute?
It was.
So could we double it if it's 2?
Okay. Oh, I think that means I did something bad. Okay. One time I did that, I had to shut everything down and back up. I think it didn't work. So what is it you want to double? Because I think you're on something.
I was just saying double. Well,
Oh, double the answer I got?
That wouldn't even make sense. That'd be a both one. So, yeah, we would double something. But it is I've yet to.
Okay. You can. So I was going to go through this to kind of show you like the difference. The more complicated way is you could say that 1 arrives in the first 6-minute interval and none arrive in the second. And add that to none arriving in the first and 1 arriving in the second. But it turns out it's the same as 1 arriving in a 12-minute period. So we can just do that and save ourselves the trouble if you would like.
So is it the same as
Yes.
okay.
But if you do, so we're kind of doing both of these together, but that's only because Pairboy suggested that there was some sort of doubling that would work. So we could work.
She got some snacks. She also told you terrible.
Yeah.
So these are the same. It is equivalent. So you could spend a lot more time saying one arrives in the first 6 minutes and none in the second, plus none in the first and one in the second. Or just make that's the same thing as one happening in 12 minutes. And so D and E are the same thing. Okay, so we need to change something. Okay, so now it's a Poisson. What's my average for 12 minutes? 2. It is 2. So it's a Poisson. X is distributed Poisson with 2 because it was 1 in 6 minutes, so it's 2 in 12 minutes. And we're just trying to find the probability of 1. You want to go to the formula or you just want to put it on the calculator? Say that one more time. Okay, so, oh, just for kicks, if it makes you happy. But it makes Emily sad, so I don't know. All right, so let's just find it for 1. So, probability, distributions, PDF. So we have an average of 2 and probability of 1 playing 0.271.